Okay, so now what we're looking at are trying to take discrete data and applying it to a normal model. So remember that our normal distributions, we're assuming that the data is continuous, meaning there are an infinite number of possibilities that exist between our 2 points that we're looking at. So what we'd like to try to do is actually also use the same sort of model when we actually have discrete data. So, if I roll the dice, I can get a 1, 2, 3, 4, 5, or 6. That is discrete data. There's not an infinite number of possibilities in between them. So that's what this node is about. So although the normal distribution is considered to be continuous, discrete data can be modeled as normal distributions to make approximations. If the data set is reasonably large, it's going to work better, and the data falls into a symmetric unimodal bell shape, it makes sense to try to find a smooth normal curve to them. So here we can see we've got we've got our intervals that we can see represented by our bars. And then we're applying, even though we've got these interval values, we're applying a normal distribution across it. So our note says we must account for approximating a discrete outcome experiment with a continuous distribution. This is done by treating each outcome as a unit interval, and we'll explain what this means. For example, in an experiment where x is a discrete random variable modeled by a normal distribution, so again, let's imagine with x less than or equal to 5. Let's assume we're talking about rolling a dice. So the idea that if x is less than or equal to 5, we're going to model that by x being less than 5.5. How does that make sense? Well, let's imagine that this is, I could roll a 5, I could roll a 6, I could roll a 4, I could roll a 3. So this is my 3, 4, 5, or 6. Well, these are the only possibilities that would exist because it's discrete data. But we know that we sort of have like a normal curve. So really what I need to be doing is I need to be measuring, if I'm talking about a 5, I'm talking about that value right there. Because I need to make sure that I'm accounting for this portion of the curve. Because in fact, the area under the curve for just a value of 5 has no width. So the area would in fact be 0. So I have to give it width. And because it's discrete data, I'm going to extend halfway to the next discrete point, and halfway down to the previous discrete point. But in this case, I'm taking a look at x less than or equal to 5. So my 5 is sort of denoted by this area, but of course I'm interested in everything less than that. So what I'm really going to be using is on my distribution curve, I'm going to be using the value of 5.5. In this case, where I'm talking about the probability where x is equal to 7, that was sort of how I started off with. I think it's easier to think of this one actually. So I could have a value of 5, a value of 6, a value of 7, a value of 8, a value of 9, whatever my data is. If I'm talking about 7, I'm not just talking about this value here because I'm discounting the entire area here in blue, because between 6 and 7, if I don't count that, well, my data is not going to be accurate. I need to make sure I'm accounting for everything under the curve. So what I'm going to be doing is I'm going to go halfway below my value and halfway up my value. So if I'm talking about 7, I'm going to be talking about this entire section underneath my curve, which is, of course, from 6.5 up to 7.5. So if we apply that, given a mean of 5 and a standard deviation of 1, solve the following. So we're assuming here that we have discrete data. This is the assumption. It doesn't say it, but because this is under the discrete section of our course, that's why we're assuming it's discrete data. We're asking for a probability of x being less than 3. So we've got some value of x is 3. Because our mean is 5. Right, this is our 5 value there. So our 3 is going to be down here somewhere. But because it's discrete data, that would be my value of 4. I've got to be talking about this section, this area of my curve. which is really, if this is 4, that's going to be 3.5 in this location right there. So this question is really going to be transferred into a normal distribution question where the probability where x is less. I'm going to pause this for a second. So I had to think about that for a second. If x is less than 3, and I choose 3.5, I'm actually sort of including my 3 value. So that would, what I started to answer would be if x is less than or equal to 3. If it's less than 3, it should not be including this section of my distribution. I should not be including that, which means that if that was 3, this is 2, I'm really going down to, sorry, I don't want to include that. I'm going down to 2.5. So I'm talking about this portion of my curve down here because my value of 3 extends from 2.5 up to 3.5. Right? This is my, I'll do it in red. This would be my value of 3, and I've got to be less than that. And my value of 3 sort of starts at 2.5 and extends up to 3.5. So when I'm asking this question, I'm going to be calculating for this section down there where x is less than 2.5. So now this becomes a repeat of our previous note where I'm now needed to calculate my z-scores for this value. So I calculate my z-score as being my data point, subtract the mean over my standard deviation. My data point is now 2.5. That's what I'm concerned with. Subtract my mean, which has a value of 5, and I'm dividing that by a standard deviation of 1. And this gives me a z value of minus 2.5. The fact that it's a 2.5 and my x value is a 2.5 is completely unrelated. It's a total coincidence. Don't think that those need to be the same. It's just a coincidence. It's the same value. So I now have my z value of minus 2.5. I need to therefore say that the probability that my x is less than 2.5 is the same as my z-score. The probability that my z is less than minus 2.5. So I need to look on my chart. What is the z-score of minus 2.5? Z-score of minus 2.50 occurs right there, 0.0062. So that gives me 0.0062, or in other words, 0.62%. What about the probability that my x is greater than 3? All right, so if it's x is greater than 3, this is again my 5, this is my 3 value. We think about that 3 value as extending from 2.5 to 3.5. So I'm interested in the value above that. Right? So this area there is going to be 3.5. So I'm really looking for, because it's discrete data, I'm saying that the probability that x is greater than 3, if I want to normalize this and pretend it's continuous data, I'm going to say that's the same as finding the answer of x being greater than 3.5. That becomes the point that I'm interested in. So I need to calculate my z-score, assuming a 3.5 value, x minus mu over standard deviation. My x is a 3.5, subtract my mean of 5 over standard deviation of 1, and that gives me a z-score of minus 1.5. So now I'm looking for a value above 3. I'm looking to the right of my curve. So my probability that x is greater than 3.5 is equal to the probability that my z-score is greater than minus 1.5. Our z-tables are for data below our values, so I've got to do my 1 minus the probability that my z-score is less than minus 1.